Hi folks again. Today I'm going to talk about three topics which are directly related to metric spaces, and those are convergence, and then the second one is Cauchy sequence, and the third one is completeness. These are the topics which are directly related to metric spaces, and you have to know them, the concept of all of them, to be able to deal with metric spaces more somehow deeper. Let's go to the convergence definition. Of convergence of a sequence. You may also have heard the limit, which is also it has the same meaning as the convergence. Okay, a sequence xn, which is the n is the index, belongs to natural numbers in a metric space. And we know from the tutorial on the metric spaces that metric space is a pair of a set, and a metric on a is said to converge or to be convergent if there is an x belongs to the set x such that the limit of the distance between the elements of the sequence to that limit of the sequence when n goes to infinity is equal to 0. And x is called the limit of xn, and we may write it down like a limit of xn n to infinity equal to x. Okay, let's see this definition. First of all, you have noticed that the definition of convergence, it is in a metric space. Then you should have a metric space, because the definition is based on the notion of distance. Then you should have a set and a distance between two elements of the set. And also something which is really important in this definition is the limit of a convergent sequence should be in the set of x. Okay, these are 2 points that I thought is really important to have in mind when dealing with the convergence of a sequence. Okay. Let's go to another concept that we need, and it is called bounded. Boundedness. Okay, what is this concept? We call a non-empty subset M, which is the subset of X, a bounded set if its diameter, which I show it with delta of m, which is based on the definition is supremum of the distance between any two elements belongs to m, is finite. And using this concept, we call a sequence xn in x a bounded sequence if the corresponding point set is a bounded subset of X. It means that if you have points, like these are the points of the set, and this is the M, and this is the X, then all of the point set of the sequence belongs to M, and M has a finite diameter, or I will call radius. Okay, I think that the definition is simple. Let's go to a lemma. Which is the, I call it boundedness and limit. Okay, I will just mention it quickly. It means that if you have a convergent sequence in X, then you will have boundedness, and also you will have the uniqueness of limit. Okay, and yeah, that is quite what I wanted to say. Is just when you have a convergent sequence in X, then you have the boundedness. And it is really easy to prove this one. I will prove it here. It means that when you have xn, which goes to x, it means that for every epsilon greater than 0, then you will have such a n belongs to natural numbers. For every n greater than or equal to n, you will have the distance of xn and x is less than epsilon. Then if you choose epsilon equal to 1, then you will have, for every n greater than this n then you chose, then you will have the x and x less than 1. Then if you choose, if you choose a of maximum because of the x1 x and go to the xn x, then you can easily follow this from this point to prove that actually the diameter of all the points of the sequence is finite. Like it belongs, all of those points belongs to a set M, and the diameter is less than this value A. Okay. Check, it's super easy to prove. Okay. Let's see what we have to cover moreover to those topics. Yeah, it is about completeness and the Cauchy sequence. Okay, completeness is a property. I will just it is an additional property which a metric space may or may not have. It means that we can have metric spaces which are complete, and you have metric spaces which are not complete. Just as an example, we know that our real line and C, which is the complex plane, they are complete. I will later talk about what is the meaning of the complete. Okay, before going to the completeness, I should say that we need a tool to use to show the completeness. And what is the tool? It is actually a sequence called the Cauchy sequence. Cauchy sequence is a property of a sequence. What is the meaning of that? It means that, let's go to the Cauchy sequence. Cauchy sequence. Okay. The definition of a Cauchy sequence, it is a sequence Xn in a metric space. Then so far nothing is really different from a normal sequence, is said to be Cauchy, or sometimes called fundamental, if for any epsilon greater than 0 there is an n, which is the n is a function of epsilon, such that the distance between xm and xn is less than epsilon for every m and n greater than n. It means that if you have like points of the sequence here, assume that this is the n that we mentioned. For after this threshold, for any of these points, the distance between them is less than epsilon. It doesn't really matter if like between this and the other one, like this and this is less than epsilon or something like that, because for every m and m greater than n, then this distance is less than epsilon. Okay, now you may ask yourself, why do we need Cauchy sequences? Well, we need Cauchy sequences because we want to define a complete space. Okay, then this space X is said to be complete if every Cauchy sequence in X converges, which we know that it should be an element of X. Okay, then now we know that why do we need Cauchy sequences. And yeah, if we have a Cauchy sequence, and for every Cauchy sequence in a space it converges to an element of the space, then the space will be complete. Then a metric space, moreover to have the properties that I mentioned in the metric space tutorial, it may have the completeness, or it may be incomplete. For the space, metric spaces which are complete, as I mentioned, is the real line and C, or I will call it R2. Or you can prove that it is also Rn also is complete. Okay. If you want to see that, what are the, for example, incomplete spaces? I should examples of incomplete spaces. These are omission of the point A from a real line yields the incomplete space R less. Okay, and something I would like more interesting is this omission of all irrational numbers from R. Can you guess what we'll have after that? Yes, we will have the Q, the rational line. And this is not complete. It is incomplete. Okay, these are two examples for the incomplete spaces, and to conclude this tutorial, I will give you a theorem. It is saying that every convergent sequence in a metric space is a Cauchy sequence. Something you should be really careful about is it is saying that every convergent sequence is a Cauchy sequence. Then this is from left to right, but it is not true from right to left. Then you can prove it super easily by saying that if xn goes to x, then for every epsilon we will have n, which is a function of epsilon, such that d of xn and x, the distance between x and x is less than epsilon over 2 for all n greater than n. Then using the triangular equality, we know that d xn is less than or equal d xm and x. We know that x belongs to, because it's a convergent sequence, x belongs to this space, plus d x and xn. And we know that it is less than epsilon over 2 plus epsilon over 2 epsilon. And we should be careful here, and this both m and n is greater than n. Okay, and you see that this is the definition of a Cauchy sequence. Then it's checked. Okay, well, this is the last part of this tutorial, and in the next one I may go over some of the more interesting examples of a metric space, incomplete metric spaces, incomplete metric spaces, which are useful for practical reasons, like in electrical engineering or like physics, and in applied science. Okay, folks, good luck. See you next time.